Notice anything strange? Under the influence of gravity, things move in an odd way. If something starts moving because of gravity, after, say, 1 second, it will have traveled some distance. Now, interestingly, during the next second, the distance it will travel will be 3 times as far as it moved during the first second. During the third second, it will travel 5 times as far, then 7 times, then 9 times, 11, 13, 15. Now, we used seconds, but it doesn't matter what time interval you use. You will always find this pattern, the odd number rule, hiding right there within the very phenomenon that keeps us on Earth are the odd numbers. More like God numbers, right? Is the odd number rule the face of the universe looking back at us? Well, here is something that Galileo wrote. Philosophy is written in this grand book, I mean the universe, which stands continuously open to our gaze. But it cannot be understood unless one first learns to comprehend the language in which it is written. It is written in the language of mathematics, and its characters are triangles, circles, and other geometric figures without which it is humanly impossible to understand a single word of it. Without these, one is wandering about in a dark labyrinth. I am gaining velocity at a constant rate, spelled with odd numbers. How? Well, what's an odd number? The concept of oddness comes from the observation that sometimes when you have a bunch of things, everything you have can be paired up. But sometimes that can't happen. Now, when it's possible, when you can pair everything up that you have, it is said that the number of things you have is even. If you can't do that, then the number of things you have is odd. Now what this means is that the number of objects in an even group is equal to 2 times n, where n is just the number of whole pairs that you have. So n is any whole number. N could be, for example, 50, giving us the even number of 100. Point is, 2n is the mathematical way to spell even. If I add just one more thing, the amount I have is no longer even, it's odd. If I add yet another thing, I've added another pair, n has gone up by 1, and the number is even again. This means that an even number plus just one more will always be odd. Now that we know how to mathematically spell odd and even, we can move on to moving. If you and me hugged, well, that would be wonderful. We would both get so much out of it. But if during the hug you suddenly ran away from me while yelling, "I'm leaving you at a velocity of 2 meters per second," well, I would be devastated. But I would know that deep down you still cared for me because you told me your velocity. And if I know your velocity, I can know just how far away you are from me at all times. All I have to do is take your velocity and multiply it by the number of seconds that have elapsed since you left. Now take a look at what a graph of your velocity would look like. Here we have velocity in meters away from me per second, and we have time in seconds since the hug ended. Now, if your velocity is 2 meters per second and that persists, then here's a graph of your velocity. But look at this. After a number of seconds have elapsed, like after 1 second, the distance you are away is just the rate times the time elapsed, 2 times 1. Well, that also happens to be the area of the rectangle bounded by a line coming up from the time, your velocity graph, and our axes. Well, that's pretty convenient. After 2 seconds, you are 2 times 2, 4 meters away from me, which is also the area of this shape we've created. After 3 seconds, you are 3 times 2, 1, 2, 3, 4, 5, 6 meters away. It's always the area. Well, that's pretty convenient. But let's change up the story. What if we hugged and it was great? I mean, just almost not even a hug, like something new is being invented here. But then, during that, you suddenly leave. You run away from me. And while you run, you yell, "I am leaving you at an ever-changing velocity." Well, I would say, you know what? That is a lot less helpful. Now let's say that this changing velocity you have that I don't know happens to be an acceleration of 2 meters per second per second. What does that mean? Well, that means that your velocity is getting bigger by 2 meters per second for every second that you run. It would look like this on a graph. You begin hugging me with no velocity, and then 1 second later, your velocity is 2 meters per second larger. So 2 larger than 0 is 2. That's your velocity after 1 second. After 2 seconds, your velocity is 2 larger still, so 4, and then 6. Your velocity graph would look something like this. But now here's a question. If you're moving like this, is the distance you are away from me at any given time still just the area of the shape bounded? It's harder to see that because you don't maintain any single velocity for any amount of time. Your velocity is always changing, so we don't have nice rectangles. But we can see that it is true by putting ourselves in my shoes. Abandoned, alone. I don't even know your motion. I don't even know how you're accelerating. It's very scary. But I can decide to take matters into my own hands and measure your velocity as often as I like. Let's say that I measure it just once. I measure it after, let's say, 2 seconds. All right, wonderful. Now the question I want to answer is how far away you are after 3 seconds. All right, so I have this measurement. I know that you were traveling at 4 meters per second. Well, I mean, look, if you're going 4 meters per second for 1 second, then that's a rectangle like this. And it's got an area of 4. But you're not 4 meters away, are you? You're a lot further than that because you weren't traveling 4 meters per second for this entire second. You were at all times actually traveling a bit faster. And I'm totally forgetting all the distance you covered before my measurement, which is not 0. Okay, so clearly I need to measure your velocity more frequently. So let's say that I measure your velocity twice during the 3 seconds I'm curious about. Let's say I measure it after 1 second and then after 2 seconds. Well, now I can imagine rectangles here. This one is 2 by 1, so it has an area of 2. This one is 4 by 1, so it has an area of 4. 2 plus 4 is 6, but you're a lot more than 6 meters away as well, because you weren't traveling 2 meters per second this entire time. You were actually speeding up, covering more and more distance. I'm totally forgetting all the distance you covered over here. Basically, this method will always leave me short. But the more frequently I check your velocity, the better things get. Take a look at this. Oh yeah. Oh wow. As you can see, the more frequently I check your velocity, the closer my calculation gets to being based off of what you really did, your actual motion. But also, the more frequently I check your velocity, the closer the combined area of all of my rectangles gets to simply being equal to the actual area bounded by your velocity curve. Which means that the area under your velocity curve, even when your curve is like this, is still totally the distance you are away from me. Now let's take this knowledge and apply it to the odd number rule. Before people knew how things fell, there were some pretty good guesses. For example, if the reason things fall is that they have within them a desire to be in their own proper place, in this example, the table, well then maybe the closer this object gets to the table, the more excited it is to be there and the faster it goes, in which case its velocity would change over time like this, getting steeper and steeper and steeper. But Galileo didn't think that. He believed that when objects fell, their velocities increased at a constant rate. So graphed like this, their velocity would just follow a straight line. Let's draw a straight line. Beautiful. Now, let's divide this graph up into strips of equal time. Perfect. All right, now, as we know, the areas of the shapes we have bounded here are the distances traveled during their respective time intervals. So what's the area of our first shape here, a little triangle? Well, we don't know what it is. We don't have any actual markings here on our axes, but that's fine. It doesn't really matter. We'll just call this 1. So in the first second or the first time interval, our object traveled a distance of 1 unit of space. Perfect. Now, how far did our object travel during the second time interval? Well, that distance will be equal to that area. Well, what is this area? Well, one thing we can do to make this easier is to divide the shape like this. Now we have two shapes, a triangle and a rectangle. This triangle has the exact same area as our initial triangle. That's because they are congruent triangles. They both have the same base length, and because this velocity line has a constant slope, it rises the same amount per time elapsed all the time. So their heights are the same, and they're both right triangles. Their areas are the same, so the area of this space is the area of that triangle plus the area of this rectangle. What is the area of this rectangle? Well, one thing we can do is divide the rectangle in half with a diagonal like this. And look what we've created. This triangle has the exact same area as our initial triangle. It has the same height, it has the same base, they're both right angles. And look, the same goes for this one. It's a right triangle. Its base is the same as this base, its height is the same as this one's height. Gosh, this is just the area of the initial triangle, but twice. So we have two of them, and we have two of them one time. Okay, perfect. Now let's move on to finding the area of that shape. Once again, I can divide this shape like that, and now I have a triangle, which, as we know, has the same area as our initial triangle right here. So we have that area, 1. And then we also have, look at that, 2 rectangles, which, as we know, we can divide in half like this, giving us now 4 triangles equal in area to the initial one. So what we've done is we've taken the initial area and we have doubled it, well, once and then twice, so 2 times. Now, as we continue doing this, we find that we're always adding 1 more of our original areas, and then we're always doubling that original area 1 more time. Here we've doubled it 1, 2, 3 times, doubled 3 times. Well, look at this pattern. Right here, we can think of 1 as being equal to 2 times 0 plus 1, can't we? Well, these numbers are whole numbers, and they're just going up by 1, 0, 1, 2, 3. This is all of the general form 2n plus 1. That is how you mathematically spell odd. So the odd number rule is not some kind of magical coincidence. It's just what happens when an object's velocity increases at a constant rate. The answer was right there in front of us all along, written in the mathematical language of the universe.